let's try to prove it. I'm gonna so once again, let me give you once again the definition so that everything is in one place. Always a good idea when you do a proof. Have things that you need or gonna need in one place so that maybe you're not gonna even go elsewhere for reference. So especially in the beginning of every theory, that is the case. So you have one page and you are the second page of the setup, and then the next page you do a few proofs. So that's what we're doing here. And so the definition once again, so XZ metric space. U is called open. I think I already did it 3 times. Well, okay, so I'm not gonna do it, but yeah, I did it already 3 times right here. Okay, so I took that definition with right here. This is pretty much the original definition right here, and with a particular choice of those parameters x and r. So U is that set that you're supposed to deal with, and that is given. But then there are 2 parameters that might be there, might have names, and the names are x and r. Then if you go to the next open set, then you'd better change those names in order to not to be confused. Okay, so I'll do the same with pictures. So once again, having these 2 pictures together may be not such a good idea after all. So I'm gonna copy and paste. Okay, and one more time. Okay, so they exist separately first, and then they put together. Okay, so the first picture will be entirely about U. So we'll just erase everything we don't need. Okay, so this is gone. There is no V. Okay, so this is gone too. Yeah, I think I'll erase this as well. Oops, like this. Okay. Okay, so, and the definition is the first line. Here I will erase all about U. Okay. There's no intersection. Okay. Okay, so whatever the bottom part, it does not exist yet. We still have to figure it out. So this is what we do have. We have U, and every location within U, such as X or Z, just the letter, what do they have? They have some kind of a circle or disc ball that fits inside of that set. So it could be large, it could be small. Okay? So nothing else. Then the second line, so that's the first line, like this. There is no V. Okay, and then the second line goes here. That's about V. So once again, every point within the set B has a ball around it, like this. So it around it that fits inside of V. Okay. Now, what is that we're trying to establish is the last line and the last picture, which means that if that Z happens to belong to both of the 2 sets, then there is a ball around it that fits inside of the intersection. Okay, that's the bottom picture. Okay, so as you can see, I intentionally made these 3. It's the same point Z. Okay, indicating the one that belongs to the intersection. But I intentionally made those circles different in order to emphasize that they could have different radii. We have 2 different statements. We have 2 different pictures in 2 different situations, and I used the different letters to deal with those points. So the BXR over there is the generic situation within U. BYS on the right is generic situation within V. Okay, but then what we actually want is Z. Okay, so if we combine these two situations together, then that's the idea that if a point Z belongs to both U and V, it will satisfy both of these properties. So that's the good news. both of these properties will be satisfied. So literally, I could just I could do exactly that. Just try to make progress in that direction. Okay, so that's the question mark, is how we get there. It still remains. But what if I try to proceed? So now suppose Z belongs to the intersection, then both are satisfied. And well, let me just write out what that means. So then it means that, remember what we're trying to establish is what's at the bottom. So we could think one point at a time, and I do. So I I call it Z. So pick a point Z in the intersection, and then we have to prove something about it. So at the bottom is just, that's what we try to accomplish, but really we want to do it with the material that we have. So let's try to make progress. So I'm going to write both of these two properties at the top for this point Z. So there, I don't have to say for every X anymore, or for every Y, because now we have the same point. The rest, however, hasn't changed. Okay, so let's say number 1, number 2. I'm rewriting number 1, and what it says, there is, I'm rewriting, there is R greater than 0, such that BZR is inside of U. Okay? Okay? The ball around Z fits inside of U, which corresponds to the picture on the left. Okay? What corresponds to the picture on the right, it's once again about Z. There is an S greater than 0, such that BZS is in V. Okay? So the two properties are right there. You can see that everything now is almost the same, except R and S. These are possibly two different balls, because R and S could be of different different radii. Okay, so we have two, and each of them, you can imagine. Let me try to make that point. Let me try to make that point of what is the issue. What is the issue here? If you can tell. Just move. So I guess what I'm asking is, we need one ball. How do we make the center is the same? That's the good news. But we progress from the first two lines to the last two lines, and we, instead of having two centers, X and Y. Okay, that is a typo over there. It's supposed to be Y over here. So instead of having two centers, X and Y, we have now one. The difference is there are two different radii. Okay? We know that we need only one. How do we make two from one? One from two, I'm sorry. We have two balls. We want to make one. So let me take that picture, and from the left and from the right, I have my point Z here, okay, and then there is one circle of radius R, so this is BZR, and there is the other one possibly smaller, or not, we don't know, but it doesn't matter. We have the other one, which is BZS. So that's where we are right now. We also have no idea how V is related to the intersection. We only know that the first one is inside of U, and the other one with inside of V. Okay, we need to end up with, which is what's at the bottom, we have to end up with one ball, say disk. Let's think two-dimensional. This is really the two-dimensional situation. Is simple enough for us to face all the difficulties of this proof. So how do we make a disk that would fit, a disk around Z that would fit inside the intersection? So the first one in purple, it is this one, BZR, let's say. Okay, as you can see, it's entirely lies inside U. Okay. In the meantime, this one is B, not this one, but this one, BZS. It lies entirely inside of V. But we need a one circle, but small enough that it will fit inside the intersection. Of U and V. Look at the bottom. That's what we're after. So, can you suggest a T? So T is what we are after, the radius of the new circle. So, choose the radius of the new ball, T equal to, okay? Can you suggest anything? Well, you could actually, if you try to guess how you make a number from 2, you have R a positive number, S a positive number, you need to find T also a positive number. There aren't too many ways to do it. If you think about it, and so you can just try to guess. Okay, here's a hint for you. It's one or the other. And we actually do have 2 choices for T. It should be either R or it should be S. Which one?
R.
Why?
Because it's the outer circle.
Right, except what? S because it's, see?
Okay.
Okay, because it is inside, and inside is better because small is better.
Oh, okay.
We're trying to fit the new circle inside of the intersection, so the small is better.
Oh, okay.
So, okay, so since this picture is actually arbitrary, I need to pick S if it is small, or R if it is small. So what do I write here for T? So if I don't know which one is larger, which one is smaller? There is a way to, how do I choose the smaller of the 2 numbers? What do we call it? Okay, let me just write the words. So let. It's always, you know how you use notation if you don't have to. Let be the smaller of the 2, R and S. Okay? So you don't have to use notation. Notation I was trying to apply is minimum. If you don't remember, they're just as good. So we choose T to be the smaller of the 2 numbers, R and S. So then what does it mean? If T is smaller, it means that, what does it mean? It means that B Z T will lie inside of both of these, right? It will lie inside of B Z R, and it will lie inside of B Z S because it's smaller. Same center, smaller radius. Okay? Why is it important? Because according to those 2 statements in the middle, BZR is a subset of U, and BZS is a subset of V. What is the next step? they do intersect. We know that they do intersect. So at least the intersection at least contains the point Z, so they do intersect. That's how we started with Z. That is an element of the intersection, so it's not certainly not empty. So so how do we get to the intersection? We combine these two statements. How?
Well, they intersect at least T amount, right?
Well, we don't care about R and S anymore. What can we say about BZT? So what follows from these two statements? This?
BZT is a subset of the intersection of U.
That's right. So BZT is a subset of U and a subset of V, which means a subset of the intersection. What's the next step? What's the next step?
What are we trying to prove?
It's right there, right the next line
Okay.
in brown.
So we're trying to prove that that is an open set?
Yes. The intersection is the open set. That's our theorem. Okay. See?
Yeah.
Okay, so so that is I put it at the bottom, so we gradually we're approaching that situation, and seemingly we are kind of close. So what's the last step? Last step. So what we have proven right now, that last statement over there in green, and the statement that we're after is in the next line in brown. Compare what we have proven here and with what we were after, the next line.
So is this going to be... Wait, never mind.
Well, just compare. Do you see that green line that we just proven? Do you see that anywhere else?
At the end of the...
At the end, okay. We have this.
Yeah.
Okay. Anything else? Well, another one over here. We started at Z. We started with over here with Z. Where was that? Over here we started with Z in the intersection. Okay, Z is in the intersection. So we picked arbitrary Z in the intersection, and then we proceeded on. So the only thing that remains is, have we found, that's the bottom, to complete the picture, is what's at the bottom. So at the bottom the question becomes, do we have that T? Yes, we found the T too. So that T, where did we found it? Right here. Let T be the smaller of the two. That is the moment of when we found T. And we say that indeed that's how we know that there is a T. We pointed it out. So the requirement was to demonstrate that there is a T, and we did. We not only we said, we pointed it out what it's supposed to be. So if those R and T, R and S that came from the openness of U and V, if they were given, and they were, then we expressed T in terms of those two, and thereby we have found it. Okay? So what's the last step? Party. Well, next step is a party. We realize we have proven everything and we are celebrating. That's all. Right? You see it that we were done?
What's the point of the X?
Of the X? The X was just a way to write out the definition of U being open. So we're starting that's the step number one, write the definition. for U and V. So that's how you got two statements. Okay? And then what does it mean? It means exactly what it says. And so for every x, there is such an r, and for every y, there is such an r. But if we pick an element that belongs to the intersection, then both of these statements are applicable. And therefore, for that z, not only there is an r, but also there is an s. So there are two of them. Okay, and that's why I did this rewriting over here. Okay, so they still exist apart from each other, but the point is the same. It is z point in u on the left and z in v on the right. Okay, so that's that. And then that was the idea. That picture in the middle gave us an idea of what we're after. And we're after a disk that would fit inside the intersection. So the smaller it is, the better. So that was just an idea, and we tried. Does it work? Okay, let's try it. We let t be the smaller of the two. In other words, as so t is equal to minimum rs. Okay, and then we see what it means, and what can we say about this smaller disk around z? And these are the two things we can say. It is a smaller disk, so it fits into the bigger disk, either one of the two bigger disks. And those two bigger disks are inside of u and v respectively. So that's those are the two lines. And then we put those two lines together, and so that same set, BZT, is a subset of, lies inside of u and v simultaneously, means that it lies inside of the intersection. Okay, and so this is how we proceed, like this. So we just put these things together. As you can see, I broke it into three parts, and those three parts gradually have appeared through our proof. So that statement that is in brown on the right is pretty much the summary of what we have accomplished. We started with z, we found t, and then we demonstrated BZT is a subset of u intersection v, which is, that's the last step over here. Over here we arrive at the definition. That brown line was in fact written, it was written yesterday as a matter of fact, was written as the definition of u intersection v being open. So that ends the proof. This is just an illustration. Illustration of the proof is here. Okay, when you see a proof, there's several ways. If you're not entirely sure about it, there are a couple of ways to deal with it, or both. One is expand, provide more details, or you streamline it and you compact it. Okay, so if you want to compact it, I think I have provided details. I just didn't write them out. So that those little explanations that I spoke but didn't write. So you might try to write them, and that may make the proof longer. But it's a good exercise. So to provide a little detail, so every time if your question transition to the next step, explain it in writing. Okay. On the other hand, you can try to compact it into a one line, maybe somewhat long line, but of proof, and so you might try. You might try it. So streamline. How do you streamline? So this proof was a little bit part of the proof was also the discovery process, the analysis, and so that's why it was longer in it. That's why it is not streamlined. But once you have the proof available, then you can try to streamline it. So then you start at the end rather than in the beginning. You start with what you are trying to prove. So let's try that just once again for practice. So that statement over here is what I want to prove, and then I start with z. So then, if you are streamlining the proof, you do not write the definitions. You invoke them whenever necessary. So you start with just z being the intersection, and that's it. So all the parts are here. You just might try to put them in a more compact form. So let's see if it works out. So proof 2. So take z in the intersection. Okay. Then z belongs to u Z belongs to V. You can, when you do streamlining, you might enjoy putting a lot of quantifiers and symbols so that it will be even more compact. Okay, so like this. And then BZ, I keep switching between capital and not capital. So let's keep it capital. I'm not sure why it's supposed to be capital. Is it capital? It is capital. Okay. Well, anyway, Z belongs to U, Z belongs to V. So BZ R is in U, and BZ B is in V. For some R, that's not a V. It was an S, right? So I use the same notation, S. Greater than 0. Okay, the next step is let T equal minimum, R and S, then BZT intersection B, hold on a second, that's not the one I'm saying, BZT lies inside the intersection, right? The intersection of V, the end. So if you're looking for a short proof, this is it. So probably both of them are valuable. Details or no details, it's like zoom in, zoom out on a map. So if you want to see the continents, you zoom out, you step aside, and then you don't see those little letters, you don't see the rivers, you don't see the cities. If you want to see the big picture, that's the big picture. Or you try to, sometimes there are maybe how do I get from North America to South America, and you have to zoom in and make sure that there's that little tiny, kind of narrow passage that it does not break. Okay, so that Panama Canal part. So is there a bridge there, or a highway? So then you have to zoom in, and but the idea, the big idea, and the outline is here. This one actually has pretty much everything there, but it's hard to write proofs like this from scratch because then you have to see it in your head at once. So that's why you frequently write proof more like this when you are exploring this proof. You are exploring rather than just writing it. So you write all the definitions so they would be in front of you. You were writing as we did starting yesterday. Remember, we put at the bottom what we were trying to discover. We also tried to put pictures to provide us with ideas. But ultimately, this is the ultimate proof when you don't need any pictures, you don't need the definition. They're there, but just implicitly used. So once again, start with Z in the intersection, then it belongs to one and the other. Then according to the definition, a ball around that point also belongs to U, it belongs to V. And then you take the smaller of the two, and that ball will fit inside the intersection, the end. Okay? So any questions about this proof?
You could use the same approach to prove the same set, right?
The same set? What do you mean? The same set?
Like, that they're equal, you just prove that they intersect, or not? They intersect completely.
I'm not sure what you're saying. This is the theorem that we're trying to establish, that the intersection of open sets, of two open sets, is an open set. So, well, if they're equal, they're equal. It's the same set, so there is nothing to prove. Well, so let's shake the tree a little bit. So, the converse. First state the converse, then think is it true or not. you state it? If U and V are open, then U intersection V is open. What's the converse? If then is replaced with the arrow goes in the opposite direction. So anybody would like to state it?
And that just if the intersection of U and V is open, then U and V are open.
Right, that's the converse. Okay, is it true?
Yeah. No?
No. So anybody would like to think of an example in dimension 1 why it's not open? So we have two intervals, or rather we have two intervals that intersection of which is open. Do those two intervals have to be open? Well, say this is U, and this is V. Okay, so the endpoint, the other endpoint is included, so which makes U and V not open. But if you take the intersection, it will be an open interval, right? Like this. Right, so it doesn't have to work out this way. Well, there is a more interesting question. So I'm sure you would have discovered that pretty quickly. That converse doesn't work. A more interesting question is, what if you intersect more than 2? What about the intersection of 3 open sets? So once again, so U open, V open. Then U intersection V is open. So that we know. Okay, now U, V, W open. Does it mean that U intersection V intersection W open? Yes? Okay, can you justify?
If you do like U and V, the intersection of U and V is open, and then the intersection of
Right.
U and V is
So
open.
this is open, and then you apply the theorem twice, right? So then this is also open. So intersection open and open like this. Okay, open. U and V intersection give you an open set. The intersection, we intersect one more time with W, which is also open, then gives you the open. Open. So apply my theorem twice. Our theorem. What about 4? U1, U2, UN open. If I take the intersection UK from K from 1 to N, is it open? Yes, because, or how?
You just keep theorem intersections, like applying the theorem
How many times?
any time.
N minus 1 times. N minus 1 times. So when you have 2, apply once. When you have 3, apply twice.
Like induction?
Right. It is an induction. Yes. So how do we proceed from this point on? Is there anything else to ask about this situation? So it is indeed an inductive proof, and we have, let's say, this we'll call the corollary. So we have n open sets in the metric space. We intersect them, we get another open set. Okay, so can we keep pushing? If you have n, what's the next one? And not n plus 1. N is arbitrary, so what's next? So we know this is true. Now, okay, so this is true. So what else can we do to this? We have n. What's the next? N. As large as we like. It doesn't matter how many we have. What's the next level after n? N is finite. The next level is infinite. Okay. Okay. So as long as we have finite, we are have taken care of it. We have finite, no matter how many, but if the number of open sets is finite, then the intersection will be still open. Okay. What if we keep going like this? U1, U2, Un, and on infinitely many open sets. And then we take the intersection of all of them like this. Is it open? See, I'm holding a right pen in my hand. It is right. Red pen. Red pen in my hand. Because the answer is no. So, so when you intersect infinitely many open sets, it's not necessarily open. Okay, can you think of an example? With intervals. Intersect infinitely many intervals, the intersection is not open. So we'll have a couple of minutes. Let's think about it. Infinitely many open sets. Intersection is not open.
If you have infinite sets, then would you eventually close?
Maybe. Okay, let's try to find a closed set. So let's try to find a sequence of intervals, intersection of which will give us a closed set. By the way, what's the simplest closed set? The simplest closed set? Well, the second simplest. The simplest closed set is the empty set. What's the next one? A point. A point is closed. So can you think of these are intervals? Open intervals, that is. Say A n, B n, open intervals. But this one is a point. The intersection is a point. Can you think of such a scenario? The intersection of infinitely many intervals is a point. Can you just, in your head, any kind of picture you have? Okay. Guess we're out of time. So just think about it for a little bit.